Hi everyone, in this video I would like to talk about the concepts of actor model, why was it invented and what problems it tries to solve. And I will also cover its advantages and disadvantages. So actor model is basically a set of rules and principles for approaching the problem of writing concurrent and distributed applications. It was invented in 1973 by Carl Hewitt, and it was initially inspired by physics, but later it got a mathematical basis called process calculi. But here I will be focusing more on basics of how it works in practice. The model was designed with resiliency and scalability in mind, and one of the first implementations was in Erlang, and it was applied at Ericsson to build their network router that achieved incredible 9/9 of uptime, which translates to only several seconds of downtime in a year. So the good place to start is to describe what is an actor. Actor is a concurrency primitive and the main building block for concurrent computation. You can think of it as a lightweight process. An actor has a number of key components. These are address, mailbox, behavior, state, supervision strategy, and children. First, there is an actor address, and it's the only appropriate way of communicating with an actor. It protects the actor instance from the outside world. After a message gets sent to an address, the actor model implementation makes sure that the message gets delivered to the actor's mailbox. And mailbox, it's a data structure and usually a queue. Each actor has exactly one mailbox, and it processes messages from it one at a time. The processing logic is called behavior. And usually on receiving a message, actor can do a number of things. It can send messages to other actors, it can change its state, can change the behavior, which will be used for handling the next message, or it can create child actors. The state is basically some variables, data structures that are scoped inside of actors, and the outside world can't have direct access to them. Now that we know what is an actor, let's move to a set of more high-level principles that make the model work. First of them is asynchronous non-blocking messaging. And this simply means that actors communicate exclusively by asynchronously sending messages. Sending and receiving messages is asynchronous non-blocking operation. The next is the location transparency principle, which means that we treat local and remote actors in the same way. When we send a message to an actor, we don't care where it is located physically. Whether it's on the same box or on some other host, the approach to handling communications stays the same. Consequently, it is recommended to treat all of the messages as if they are remote, meaning that any message can potentially get lost. The next is supervision and hierarchy. And this principle allows applications to be resilient. Actors live in hierarchical structure, meaning that each actor can have a parent which supervises it, and also it can have children that this actor is responsible for. Usually with this approach, an actor gets created for each task that can potentially fail. And by failure, I mean something more complex, something that can be handled by business logic. It can be, for example, a connection pool failure or some component that needs restarting. So if an actor fails, this failure gets propagated to its parent. And then parent can do a number of things. It can restart actor, can restart all of its children, or it can propagate an exception to its parent. And its parent can also propagate it, and it has a recursive nature. And this approach allows to restart the whole branches of the program. But let's return for a moment to the problem we're trying to solve, and it's called shared mutable state. So basically the problem of shared mutable state is the situation when a same object, same location in memory can be simultaneously changed by multiple threads of execution. And that can result in the broken state and inconsistency of your programs. And to avoid this problem, it is required to use locking mechanisms such as log semaphores and stuff like that to restrict that access. But as applications become more and more complex, the locking is also becomes more complex and difficult to implement correctly, and also support, test, and troubleshoot. So using locks can result in a number of potential problems like deadlocks, race condition, and even poor performance because of poorly implemented locking. So how can the actor model help here? It overcomes the problem by using shared nothing approach, and it simply puts the state that can change inside of an actor so that the concurrency is not affected and locking mechanisms are not needed, because the execution is limited to only one thread at a time. But there are a couple of important caveats in order to make this model work correctly. First is actors should not leak their state to the outside. All of the communications with an actor should go only through its mailbox by sending messages. All of the messages the actor sends must be immutable and fully serializable, meaning there is no mutable references or mutable data structures inside of them. Otherwise, it can violate the restriction of only one thread at a time having access to an actor's data. The second caveat is that one should not have blocking code inside of an actor, and while this doesn't block the sender of the message, it can mean that lengthy operation degrade the overall performance. Here is an illustration that shows how exposing an actor's internal state can introduce race conditions. Here are three actors on this diagram: actor A, actor B, and actor C. First, actor B sends a getState message to an actor A and expects its internal state in return. After that, actor C also sends a message to an actor A that makes it to run a command. Then actor A responds to actor B with its internal state. And then actor B starts to run some operation with that internal state. And also at the same time, actor A processes the do stuff command. Here we can see that they all modify the state at the same time. But what really makes the model stand out is the concept of supervision. There was initially no such concept in the actor model. It has appeared later in 90s as part of actor model implementation in Erlang. And I already said that it was applied at Ericsson to build the network switch software with incredible uptime numbers. So how did it achieve such level of resiliency? The answer is fail-fast approach. The idea behind the fail-fast is that components should not handle failures outside of their direct responsibilities, and instead let it fail and throw an exception which will propagate to their supervisor. Supervision means you have a clean separation of your business logic and recovery code. Error handling. There are two approaches to systems that never fail. First is to make all of the components protected from all possible types of failures, and the second is to have a recovery strategy. The first approach can be problematic because unfortunately it is not practically possible to protect against all of the potential failures, since it can be very costly to develop and sometimes really hard to predict all of them, because complexity grows with a number of interacting components, including the network issues and hardware instabilities. This approach also violates the single responsibility principle, because your business logic gets mixed with the recovery code. As a result, it will be hard to separate them out. The second approach is to have a recovery strategy. It means that the system needs to be fault tolerant, so that it can stay available and continue to run. Recoverable faults shouldn't trigger catastrophic failures. A failure in certain parts of the system shouldn't crash the entire system. So you need a way to isolate particular failures that you can deal with them later. Those components can be then restarted or replaced with freshly created ones. Hierarchical structure. Actors live inside of a hierarchical structure, and this closely relates to the feature of supervision. Each actor has a parent, which is responsible for reacting to its failures and can restart it or propagate the failure to its own supervisor. I want to emphasize that you should not fail on something obvious that you know or can predict, like dividing by zero, for example, because this is a part of business logic and does not require any external dependencies and unrecoverable consequences. And we're gonna finish with the criticism of the actor model. First statement is actors do not compose well. Because an actor is designed to be a self-contained entity with both data and behavior, there is no good way to inherit some of the common traits. Though it is possible, it still can be time-consuming and confusing to program with actors, because in almost any non-trivial programs, there will be many kinds of abstractions to keep track of. Another problem is the behavior replacement. The behavior is dynamic. That's why it is very difficult to perform a static analysis on it in type-safe languages, and this also makes the code optimization very difficult. The next one is that actors are still a low-level programming concept and are inherently unreadable because the logic is spread out in different places. As complexity grows, it becomes harder and harder to understand who is communicating with who without some sort of a diagram or a design guide. And the last one is that some algorithms that rely on order of messages are more difficult to implement because the messages can arrive out of order due to the environment or network issues.